So the intuition behind this problem, so solving linear equations, why might you think that quantum mechanics, so A is known, B is known, and X is unknown, and let's say that there are n variables. The motivation for solving this problem, well, this is a very common problem. You know, you want to find X is equal to A inverse times B. This solving linear equations is something that happens a lot on its own. My daughters who are in junior high school have to do this in their class, and they would definitely like to have a quantum computer for solving their linear equations. And it occurs very frequently as a subroutine for larger problems. And one thing that's happened recently is that because with the huge amount of data that's being collected in the universe, or at least on Earth by human beings, this number n, the number of variables involved in such equations, can get very, very large. It's perfectly reasonable to have things where you have 10 to the 9th variables or 10 to the 12th variables. And the problem is that the best classical algorithms run in time. Well, you're probably familiar, the one that probably everybody here learned in school, the one where you gradually eliminate variables along the way, and then you bring down the number of variables each time, and you have n variables, and it takes n squared steps. So it takes time order n squared, where n could be a big number. So for instance, nobody is going to invert a set of equations over 10 to the 12th variables soon, but it's perfectly reasonable to have systems where you have terabytes of data and might want to do that. If A is sparse, so this is called Gaussian elimination. I mean, I didn't know that until I started looking at this. But it's just, you just eliminate variables, express them in terms of the other variables, etc. And if A is sparse, so that means no more than S, which is, say, S is a lot smaller than N, entries per row, then it takes time order n log n, which is pretty good actually, because there are n rows. And so, by the way, this kind of problem occurs all the time when, for instance, you have a discretized version of some partial differential equation, right? Then, so each variable is only related to a few other variables. And this is done via what's called conjugate gradient descent. Excuse me, gradient descent. What all that means is a fancy way of saying you try out a potential solution for X, and you say, oh, it's really not good, okay? It's not very good. And you say, well, let's look at solutions in the surrounding area. We'll take a set of solutions in the surrounding area, and we'll see which ones look better. And you just move in the directions of the one that look better. And then you take your new guess, and you try out a bunch of solutions in that area, and then again you move in the direction that you went, that things are better. That's the gradient descent part. And the conjugate part simply means that you keep track of where you've been and you don't go backwards. So because it's a linear problem, actually, you're trying to minimize you minimize a quadratic functional, which is ax minus b squared. Because you're minimizing a quadratic functional, there's a unique minimum for this, and so gradient descent will actually do a good job. Okay. I mean, I'm not here to talk about the classical algorithms, but they are easy to describe, and I just tell you what the best ones are. All right? Now, why might you think that quantum mechanics could do better? Well, the really stupid this argument is, gee, I'm going to use red for quantum mechanics. So the blue is classical here, and red is for quantum mechanics. Right. I normally draw electrons as being blue, and then a famous Italian physicist who has been blind from birth told me, no, Seth, you're wrong. Electrons are yellow. Hey, yeah, it works for him, so. So, why might quantum mechanics do better? Quantum mechanics might do better. The really stupid intuition is, whoa, quantum mechanics is linear, and gee, these are linear equations, so hey, maybe we can solve them, right? Which is a really stupid argument, but it actually turns out to be correct. So, and I'll tell you how that works. And the quantum mechanical version is we have some matrix A, which is going to be a quantum mechanical operator now. And we're going to multiply it by a quantum mechanical vector. And it's going to be equal to another quantum mechanical vector. And we were going to assume that somebody gives us this B, and somebody gives us this A in some suitable quantum mechanical fashion. And we want to find X is equal to A inverse B. Or I'm going to say, rather than find, I think we should really say construct, because this is going to be a very physical process. We're going to start with this vector B, and then we're going to act on it by a dynamical process which institutes which is related to this A. For instance, if A is Hermitian, then we're going to think of A as being the Hamiltonian for a system. E to the minus IAT acting on B. So that's the kind of thing we can do. All right? So we're going to actually construct this X, and then this will give us our answer. So the question in the quantum mechanical version is, can we construct such an X? So let's just look at the accounting for this. How hard is this to do? Well, so if this is an n-dimensional problem, then we need log to the base 2. I'll call this little n is log to the base 2 n qubits. And similarly, we need roughly that for this B. Actually, A doesn't have to be square here or even Hermitian, but I'll show you in a moment how to deal with that. So, okay, so we can actually encode the problem in log n space log n. If A is sparse, so we're going to look at the sparse case, I'll tell you about the non-sparse case later, then this takes order then this exponentiation takes order log to the base 2 of n steps on a quantum computer. So actually we really have a fighting chance here. I mean, I'd like to point out how the bizarre it is that we could in fact solve this problem using only logarithmic resources, right? I mean, this says if I have a terabyte of data that I could encode everything, that's so 10 to the 12th bytes, or let's say a terabit of data, so I can calculate the numbers easily. So that's 10 to the 12th bits, because 10 to the 2 to the 10 is 10 to the 3rd. That I need 40 qubits to encode this information, and so I can only need 40 qubits and order 100 or so steps to invert this matrix over 10 to the 12th variables. So it's pretty shocking. And again, I think this is why people didn't think of this before. But I'm going to show you can do this. I better be careful not to use up too much time here. This doesn't take that long, so I mean, it's a pretty simple algorithm. I should say that when we published this, it was one every now and then, you publish something that catches the attention of some community, and this caught the attention of Slashdot. Who here knows? You know what Slashdot is? Who here doesn't know? Who here doesn't know what Slashdot is? Oh yeah. So Slashdot is one of these, internet discussion forums inhabited primarily by really annoying geeks. So I think that a lot of them are probably like, write compilers for a living and stuff like that. So they are very irreverent, and they say mean things to each other, and they discuss things at great technical depth. It's a pretty funny forum. It's worth checking out. Anyway, so when we posted this paper on the archive, a Slashdot thread started up with people discussing it, and somewhere down like person number 14 or something said, this is ridiculous. You can't possibly do this because just to read in the input takes time order n. And the next person on the thread said, "You moron, you idiot. If you'd read more than log n of the paper, then you would find out how they do it." Of course, this brings up an issue, which is you also can't read out the output, right? Because it has n variables. But what you can do is, in the end, you can take some kind of expectation value of the following form. mx, where m is some operator. So you can't figure out the exact entries of x in time log m, but you can evaluate some expectation value or global properties of this operator. Okay? So that's how this operation works. Let me just switch to green to show you what's going on here. So this is an encoding step. This is right here. This is our goal. And this is the kind of thing we're going to do in order to find the answer. And this is evaluate the answer. So these are the steps. Okay? Everybody happy? Do people have questions before I tell you how this algorithm works? Anybody want to object strongly or weakly or start their own Slashdot thread? Okay. All right, so, then I'll just tell you how it works. So the first step is we're going to assume A is equal to A dagger. This actually, this says, oh, you're cheating, you're only using square Hermitian matrices, but it's very easy to solve the problem in the following context: 0, A dagger, 0 acting on 0, X is equal to B, 0. Right. And then actually I can, if I solve this implies that Ax is equal to B for any A. Including A's that are not square. They could have, there could be more. The problem could be either over-constrained or under-constrained. Okay? So everybody happy with that? So now I'm going to assume that A is Hermitian. All right, A is sparse. S much less than n entries per row. This implies that, again, as I mentioned there, that we can perform if we're given B, we can do e to the minus AT acting on B, and this now becomes essentially just simulating the action of this local Hamiltonian. This means that A equals A dagger is local. So it corresponds to a Hamiltonian where things are only where the variables are only interacting with local variables. And it's been known for quite a while now that if A is a local Hamiltonian, I proved many years ago now, like in 1996, that you can do this in time log n. And it's been known that for maybe 8 or 10 years that if A is sparse, then you can do this for any sparse A, as I mentioned over here. Okay. So now let's come up with a trick. So one way to suppose that suppose we knew how to diagonalize A. If you know how to diagonalize a matrix, there's a very easy way to invert the matrix, because once you know the eigenvalues, the inverse matrix is just the one where the eigenvalues are inverted. So if we could diagonalize A, so A is equal to, so let's write it in the following way, U dagger is equal to lambda 1 up to lambda capital N, 0, 0, then this implies that A inverse is equal to U dagger lambda 1 inverse up to lambda N inverse 0 U. As you can easily see by multiplying these two A and A inverse together in this diagonal form. I'm sorry if you can't see that in the back. Anyway, if you can't see it in the back, you just get the eigenvalues, you invert them, and that gives you the inverse matrix. Now, classically, this would be, this is certainly one way to solve the problem, but it's not a very good way to solve the problem classically, because classically, I think this is actually an n cubed, not an n squared, sorry. Classically, to invert the matrix, basically, the way that I remember from high school about how to invert matrices is doing Gaussian elimination. To diagonalize the matrix is as hard as doing this Gaussian elimination. So this doesn't help you classically. But now quantum mechanically, we actually have an algorithm for doing this. The so-called quantum phase algorithm. This was invented by Kitaev in around 1995 or 1996 for giving an alternative way of solving Shor's algorithm. But my graduate student Dan Abrams and I showed that this is an algorithm that allows you to find the eigenvalues. This is what Kitaev used it for, but also very importantly, the eigenvectors of A. Okay? It takes the ability to exponentiate a matrix and find its eigenvalues and eigenvectors. And I actually claim that this has been known for a very long time, much longer than quantum information, because all it really is von Neumann's quantum mechanical model for measurement, right? Because when you make a measurement, what you do is you von Neumann measurement takes a system, you make an measurement that corresponds to a Hermitian operator A, and what you get is one register. You get one register that gives you the eigenvalue of A, and then the system is left in the eigenstate of A, right? And so actually the way that this works, the way that von Neumann described it, let me just remind you, is that here I have this state B, and B is going to be equal to the sum over, we don't know what these eigenvalues are, let's just call them psi sub j. These are the eigenvectors. where this is the eigenvector associated with the eigenvalue lambda sub j. And you take another register, which basically you can think of as a particle or a pointer variable, which is initially localized at the point 0. And then you apply the following operator. So we apply A, and we tensor the momentum operator for this pointer variable. And what the momentum operator does, the momentum takes position and it moves it. Right? This is true classically. It's also true quantum mechanically. And it moves it by an amount that's proportional to the eigenvalue of A. So this is actually equal to the sum over these j, beta sub j, psi j, and then we have basically some lambda j times t. This is in I forget which page, like on page 233 of von Neumann's 1930 book on the foundations of quantum mechanics. And that's really all this quantum phase algorithm is, except that there's, the quantum phase algorithm tells you explicitly how to do this once you're given this A. Are people okay about this? This is very antique quantum mechanics in some sense, but I'm just reminding you that you can do this quantum mechanically. Okay, and I'll call this U sub phi. This is the quantum phase algorithm. Okay, are people all right? This is kind of the key step. Actually, there's several key steps, but this is a key step. All right. So everybody okay? Anybody not okay? All right. So now, once you have this, you see, of course, you have to be careful because all along the way, you have to be careful because you've encoded things into a finite number of qubits. You don't get this exactly. You only get it to a particular degree of accuracy. But I'm going to ignore all that stuff now. And at the end, I'll tell you how all the accuracies work out. But now you see, we're in a really good position to do this inversion because we actually have this eigenvector sitting here. So we have an estimate here. And so in quantum parallel, we can now do the following step. We can multiply this times a phase. So I'll call it E to, and I'll put a little delta in here. It's some small number. Actually, it could even be this t for that matter. I'll just leave it as a t. It could be the same t. No, I better make it a delta, sorry. My quantum computer looks what's in this register, says, aha, now I know the eigenvalue, so let me turn it into a phase. Because you can always turn it into a phase. You invert it. You say, oh, what's 1 over the eigenvalue? You turn it into a phase. All right. This is, of course, the key step, because actually once you realize you can do this, you'll see the rest of it follows almost directly. And now, let me go. I'm sorry to kind of wander around like this. This is maybe bad Blackboard technique. Now I undo the phase algorithm, this kind of measurement algorithm, and I get sum over j, beta sub j, e to the I delta lambda inverse j, psi j, 0. But this now is equal to e to the I delta A inverse acting on B with 0. So now we're almost there, because the only step left is if we make delta small enough, this is equal to 1, approximately equal to 1 plus I delta A inverse acting on B with 0. But it actually turns out to be not very hard to extract just this part. So some delta is small, but some reasonable fraction of the time, you're actually going to get your answer. And so the net result is we get A inverse acting on B, and the number of a number of steps that goes as, let me see if I can get this right. I think it goes as S squared, that's the sparseness, divided by epsilon. So we get it to accuracy epsilon. Excuse me for standing in the way. I know that's bad, bad board technique. In time, order S squared over epsilon log to the base 2 of n. Oh, and then actually there is another number here, which is a kappa squared. I've got this number kappa is equal to, it's called the condition number, it's equal to lambda max over lambda min. So you see, if some of these eigenvalues are really small, then the inversion becomes tricky. If one of them is 0, for instance, then you can have trouble. So it's going to take longer because the small eigenvalues, you need to take longer to find them, and then you have to be careful when you invert it. So the condition number of a matrix, and everybody, all the classical people who solve these problems, the condition number of the matrix is one of the key questions here for how long it actually takes to do this problem. I should mention that even if some of the lambdas are 0, so the problem is not solvable, that's actually still okay, because at this step right here, you can have your quantum computer associate, say, oh, well, this lambda is 0, I'm not going to invert it, and it raises a flag saying, danger, danger, small lambdas. And then, so what you can actually do is, you can even do better, you can get A inverse together with, on the part that is invertible, together with information about the part that's not invertible. So it's not really a bug, it's a feature of this. And let me see, the best classical algorithm, let me see the best classical algorithm over here, I seem to recall, takes time, I'll give you the full, for this, it's order, kappa squared s, maybe just kappa s, I don't remember exactly, over log of epsilon, so minus log of epsilon times n log n.
Can I?
Please.
Can you, I'm sorry, this is perhaps ignorant questions. Can you show in the quantum circuit way about, for example, can you in the 2 qubits,
these steps.
Yeah,
this
0 is the unselected, right? In the quantum circuit.
Yeah. So I can, but I can, but I don't have time. So it's this quantum phase algorithm. It's a very standard algorithm. If you look in Nielsen, Chuang, it's there. It just simply involves doing conditional Fourier transforms. But all it really is you can think of it as another way of thinking of it is doing just a quantum simulation of this Hamiltonian, which I think is maybe even easier to think of. Okay, so you see, I mean, there are some issues here. An important one is that you can't read out every entry to the answer, so that's a restriction. I mean, of course you can't because it would take time order n to read out every entry. If you compare these things, the dependence on condition number and sparseness is rather similar. I don't even know if I've gotten the right one over there. I'd have to think about it for just a second. Since I gave you a set of options, since I didn't actually go and prepare the talk individually, I don't remember offhand the exact dependence there. But I do remember, so here we have a 1 over epsilon, and there we have a 1 over log epsilon. So the classical one has a better dependence on the error. On the other hand, the most important thing, and the big thing is, this is n log n, and this is log n. And in fact, since it's log n, it would actually be quite bizarre. It would be very strange if you had a better dependence on the error. And in fact, you can show that since you can actually, you can rephrase computational problems in this way, you can actually show that if you actually had a log epsilon down here, then you'd be able to solve NP complete problems in time log n on a quantum computer. And that seems unlikely.
So do you repeat this process until you get complete answers, or what's the...
Right. So right here, you see that you have some amplitude of finding A inverse B, and so you just repeat the process until you get, this is actually B plus A inverse B.
Yeah, so you just need to keep repeating.
Yeah, that's right. There are all kinds of sneaky things. If you look at the longer version of our paper, this appeared in Physical Review Letters a couple of years ago, and if we did a longer version of the paper on the net. There are all kinds of sneaky things that you can do along the way in order to get this kind of this dependence that we actually get. But yeah, the short answer is yeah. You just this has some probability order delta squared to find this. You can actually turn that into a probability of order delta by sneaky tricks. But the point is that delta only goes as log n. So you're okay. Well, you have to check carefully that all these steps work. I mean, you're trying to fit something really huge into a little tiny box. And so it's got to be folded up in a really sneaky way to get it in there. So you have to check each stage along the way carefully.
What's the experimental effort situation to implement this?
Yeah. So actually, together with Dave Corey and one of his graduate students, we looked at implementing this on an NMR quantum computer. But then this kind of fell apart when he moved up to Waterloo because the graduate student stayed at MIT doing something else. So we came up, you actually need, so you have this B register.
Right.
You have the register which stores the eigenstates to some degree of accuracy. And then actually it turns out that you actually need another register here to tell you when you've got the answer. So you end up doing something that gives you have another register that says, hey, did we get the answer or not? So we figured we could invert 8 by 8 matrices where 3 qubits here, 3 qubits there, plus 1 extra qubit. So with 7 qubits, you could invert an 8 by 8 matrix, which is inverting 8 by 8 matrices is something I don't like to do by hand. So we figured that was pretty good. If you wanted to do a 4 by 4, you could do it with 5.
So you can basically use the molecule adapted by Leland van der Sijpen and so on. 7 qubit molecule.
Yeah. They're in NMR. I mean, now they're like 12 to 15 qubit molecules. So, I mean, there are technical issues that make some of them harder and some of them easier. So you could not easily, I should say, but that's a theorist talking. You could readily use room temperature NMR to perform this algorithm. And there's some group in China that's trying to do it right now, though from my correspondence with them, I'm not actually hopeful that they really understand what they're doing. Some of the things they say are like, whoa. Yeah. So, I mean, it's nice. And it's, well, I shouldn't say it's...
What's the minimum number? Can you work with 3 by 3?
4 by 4. 4 by 4. So 5 qubits, 4 by 4. I think that's the minimum number. That's what they're trying to do in China. But yeah. So
anything they can do with the superconducting qubits? That's not.
I think they're not really at that stage yet. Actually, both ion traps and superconducting qubits. I mean, in ion traps, they really have a limited ability right now to address individual ions. So I mean, people can do it. There are experiments that do it. But I think 5 qubits with individual qubit addressability for ion traps would be tough. And the same with superconducting qubits. They're trying, they've done 2 qubit algorithms, but they're not doing 5 qubit algorithms yet. So certainly the easiest way to do this, even though it would require a bit of effort, would be at room temperature NMR. But I'm hoping that the ion trap folks and the superconducting folks may soon be able to do a 5 qubit algorithm. It'd be a good test for them. Okay, so as I told you, it's actually, it's not that complicated an algorithm, and I mean it relies on kind of tried and true techniques together with one sneaky trick, right? And the overall sneaky trick is just, I think, as I said, the main reason that people didn't discover this before is because it's kind of unbelievable, right? It's kind of unbelievable. I mean, it seems like way too much that you should be able to do this. In fact, when I first started working on this, it was at the suggestion of a classical computational complexity guy who said, hey, why don't you try to solve some of these linear equations, because they actually, they take a long time and they're often the sticking point for many algorithms. And I thought, oh, well, maybe we'll get like a square root of n speed up or something like that. But as it turned out, it was log n. It was like exponential speed up. Okay, more questions about topic number 1? I actually did pretty well. I mean, it's a little more than, I started 45 minutes ago. All right, so let's vote again on topic number 2.